Here we're going to look at predicting acid-base reactions, and we're going to do it using pKa values for now, and later we'll learn some other ways to make these predictions. So let's start with an example. Let's say we're reacting this carboxylic acid with hydroxide. I recommend still when we're doing these types of reactions, go ahead and draw in your lone pairs. So we have 3 on the hydroxide, 2 here, 2 here. And what we're trying to figure out is, 1, the products of the reaction, but 2, how does this reaction lie? So the reaction could be an equilibrium, 1-to-1 between the starting materials and products. The reaction could favor the products, meaning I'll draw a long arrow to the right toward the products, a short arrow to the left. Or the reaction could favor the starting materials, where I draw a long arrow to the starting materials, a short arrow to the products. Well, first, let's predict the products, and then we'll figure out, does the reaction actually occur to the right, or are the reactants favored? All right, here we have our acid and our base. The base should be easy to pick because it has the negative charge. And what you want to do is always start by putting your pencil down on a lone pair of the base. Then draw a curved arrow to the acidic proton in the acid. And then, let me just highlight the electrons in this bond so we can keep track of it. Then we want to take those electrons out of the proton and put them onto the neighboring atom, because that proton can't have 2 bonds. So as you add electrons to the hydrogen, electrons must leave the hydrogen. So now if we track what we get here, it doesn't matter if you draw the conjugate acid or conjugate base first. So we get this product. We still have the original lone pairs, but now I've added 1 more lone pair to that oxygen, and it now has a negative charge. Plus my other product, this lone pair formed a bond with this hydrogen. So we have H bonded to OH, we have water. Now we want to figure out what's our conjugate acid, what's our conjugate base. What I recommend doing is just cover up the left side of your equation for a second. Now just look at the 2 structures on the right as a new acid-base reaction problem. So if you were given these 2 things and asked to classify the acid and the base, I think you could probably do that pretty easily. You would say that this species here that has the negative charge, that's going to be our base. This species on the right with this proton to donate, that's going to be our acid. But now we have to consider the fact those things are on the right side of the equation. So what that means is we label them as the conjugates. Okay, so now to predict the directionality of the reaction, we want to follow this principle right here. Acid-base reactions lie to the side opposite the stronger acid. So we can use our pKa values for this. And if you look up the pKa values, we have a carboxylic acid, which is 5. So look up the pKa of your acid, look up the pKa of your conjugate acid. The pKa of water is about 16. Between the 2, the carboxylic acid is the stronger acid. So what that's telling us is that this is more willing to donate a proton, and since it's more willing to donate, the reaction goes to this side. This one would rather keep its proton, so this reaction doesn't want to go in the opposite direction. So the reaction lies opposite the side of the stronger acid. Here's the stronger acid, so the reaction lies to the right. So we will circle this as our correct equilibrium arrow. Here's another example. So now we have two neutral species, so we have to figure out what's the acid and what's the base. Well, the easiest way to spot this is we have a lone pair here, so we're going to classify that as the base. And if that's the base, the other compound will have to be our acid. So now, just like we've been doing, put your pencil down on the lone pair of the base, draw a curved arrow to a proton in your acid. Then we have to add a second arrow that show the electrons in that CH bond. Those leave the hydrogen and go onto the carbon as a lone pair. So now let's draw the products of this reaction. So we end up with a lone pair here and a negative charge. Plus now we have a hydrogen attached to the NH3. 4 bonds on nitrogen gets a positive charge. We do have charge balance, so net neutral on the left, positive and a negative, net neutral on the right. From here we have the species with the lone pair and the negative charge, that's our base. Since it's on the right, it's the conjugate base. The species with the proton is the conjugate acid. Now, let's look at our pKa values and see if we can predict the directionality of this reaction. The pKa of a hydrogen on an sp2 carbon is about 44. Then, if you look up the pKa of a protonated amine, the pKa is about 10. So following our rule, acid-base reactions lie to the side opposite the stronger acid, while the protonated amine is the stronger acid. So this reaction lies heavily to the left side. So what does that mean in reality? If you were to mix ammonia and this alkene, nothing's going to happen. You're not going to get any acid-base reaction to go to the right. But on the other hand, if you were to take this particular base and mix it with this acid, this reaction would take place to give you these products.